Hi, welcome to our ordinary differential equations. Today's topic would be method of substitution. So the discussion was how do we solve an ordinary differential equation of first order. So in general, that's how it looks like. There is no recipe that is going to solve all such problems. So we are going to go after special cases that we can handle by special methods. So far we have gone through two of them, separation and integrating factor. Separation meant that x and y can be separated to two sides of equation. Uh, that applies to very special kind of equations. Integrating factor apply to the linear ones, and we had the general recipe for handling them. There's also a case of exact equation, put that aside for the time being. We are going to go after the method of substitution. Sometimes a differential equation can be relegated to the previous cases that we had by applying a special substitution. There's a long list of examples of this. Some of the names that are attached to it is called homogeneous, Bernoulli, linear, and some other cases. Briefly speaking, homogeneous differential equation means that the y prime is such that right hand side can be written in terms of ratio of y to x or x to y. And in that case, that ratio is going to be the natural candidate for our substitution. Case of Bernoulli, that comes out of a case of studying motion under drag force, a general drag force. That problem leads to equations of this type, and then we are going to see that the substitution that's going to save the day here has this particular format. The case of linear is when the right hand side, the argument of f is a linear function of x and y. And of course, the simple recipe here is just to take that interior as our substitution. And there will be some other cases, special cases, that a particular kind of substitution is going to help us solve the problem. What the substitution is going to do is to make our problem look like some of the previous ones. So these problems turn out to have multiple layers to them. You have to go through several steps to see how it all plays out. Okay, well, I've chosen a mix of this type of problems today, and we are going to take a look at them and see how we are going to attack each of them. First one for the method of substitution is for the case of so-called homogeneous equations. The idea of homogeneous is that, let me just explain what homogeneous means. If I have a polynomial in x and y, for example, x squared, x squared plus say 5xy plus y squared, you see that there's something nice about this thing. The total power of each term is just 2. If I have x cubed plus say x squared y plus y cubed, again this is homogeneous of order 3 because each of the terms is of total power 3, meaning if I multiply x and y by a certain number, the whole expression multiplies by the cube of that number. This one multiplies by square of that number. Now, if I take two such expressions, for example, x squared plus 5xy plus say y squared, and say divided by just x, say x squared plus y squared, this becomes homogeneous of order 0, meaning if x and y are multiplied by some number, the fraction doesn't change. For example, if I take x and y and triple it, numerator multiplies by 9, denominator also multiplies by 9, and as a result the fraction doesn't change. Now what we are saying is that if we are dealing with this kind of an expression on the right hand side of our equation, then we essentially have a quick recipe for handling all such problems. To make it specific, let's go after a simple case, not too crowded, not going to be as challenging as these things, and then see how we are going to handle that. So I'm going to take a look at case 1, that is x minus y dx plus x dy equal to 0. Well, if to write it in the traditional format, let's rearrange this thing. So x dy, I take this expression to the other side, so minus x minus y dx. This is same as saying dy dx. I still keep the negative there, minus x minus y over x. So that one divided by this one. Now notice this is homogeneous of order 0, meaning if x and y, for example, both of them are tripled, the fraction is not going to change. What that means is that the ratio of y over x is the only determining factor for what this thing is going to be. To see that, let's keep the minus out. Let's just divide term by term. So x over x is just a 1, and then y over x. Well, y over x is a ratio, and we are saying the right hand side is dependent on the ratio y to x only, not individually function of y and x separately. So I can write this thing as dy dx. X to x is of course 1, and this is, let's write that one first, y over x, and then so minus 1. So what I wrote here, y prime is equal to f of y over x. It means the right hand side can be written as a fraction y over x, or x over y, whichever you wish. If it can be written in that, then the substitution that's going to save the day is just take that ratio and call it v, or if you wish, take x over y and call it v. Either way. So here's the idea: y over x, that ratio is going to be called v. Another way of writing this thing is that y is equal to x times v. Who is v? Remember, y is something we are going to find, so we don't know what y is. Ratio of that to x is some function of x, as still unknown. So v is some function of x. Now I can go ahead and notice that I have a derivative here, so I better go calculate the derivative. Derivative of the first is 1 times v plus x times derivative of v, which is v prime. So this y prime, of course, is just dy dx. So what I have is v plus x v prime. Okay, so this derivative is just this derivative we calculated here. Now y over x, by our convention, that was just v, and then I have minus 1. Well, this problem, very simple. It so happens that the v's cancel. We don't always get that lucky, but, well, yeah, we get any help we can. X v prime becomes minus 1. Well, divide by x, or let's write it x v prime is dv dx is equal to minus 1. What does that mean? dv, I calculate minus dx over x on the right hand side. What happens is that this equation is separable. It always turns out that at the end of applying this homogeneous approach, if you can apply it at the end, your equation can be separated. V is on one side and x is on the other side. Well, no, you integrate, and the derivative of dv is just v, and in the derivative, well, let's just write it. So on the right hand side I have logarithm of x plus a constant. In calculus 1, missing the constant is not always such a big deal, but here without that constant the problem just collapses. You have to be careful. Okay, now what? The problem wasn't asking us to find v, it was asking us to find y. So if we go do back substitution, so v is y over x, and that is minus logarithm of x plus some constant. And problem typically asks you for finding y. So we multiply, so I get minus x logarithm of absolute value of x plus a constant times x. And that is the solution for this problem. So let's see what happened. It was written in differential form. I wrote it in the like Leibniz notation. Notice the right hand side can be written in terms of the ratio of y to x. So I take that to be my new variable. Based on that, I go ahead and calculate what the derivative is going to be, the derivative that shows up on this side. I calculate that derivative, replace the derivative with the derivative in terms of v, simplify. What I get is always going to be separable, so I apply the method of separation to that and solve the problem. So that is how to handle problem 1. Problem 2, you can look at it and say, well, it looks pretty much the same. So same approach applicable here. It's a method of, so let's remember, is the homogeneous, which means we take the ratio of the two variables as our new variable. We suspect that as you have more pieces here, what happens is that, well, in this case, in this separation step, how complicated that's going to be, it depends on the problem, and most of your time is going to be spent at this stage, and then once you go through that, then everything is straightforward. So converting to your new variable, that's the big basic idea. So that is the meat of the whole problem, that is, it can be approached this way. As far as the algebra or calculus is concerned, we have some peak to go through here to calculate the integral, and then after that it again becomes straightforward. So let's go ahead and handle the second problem, 6x. So problem 2 is 6x dx plus 6x dx plus, what did I have here? Y minus 5x, y minus 5x dy is equal to 0. So let's rearrange. So I have y minus 5x dy is equal to minus 6x dx. Write it in the traditional Leibniz form. So it becomes minus 6x over y minus 5x. As before, we are going to take, notice that this is, let me write it. Let's divide by x to make sure that it is homogeneous. Say divide by x, so it's minus 6x over x, y minus 5x over x. It's minus 6 over, do term by term division, y over x minus 5. So what do we get out of this manipulation? What we get is the right hand side can be written in terms of this ratio. How can we tell ahead of time that that's what's going to happen? If all terms here, all of them have the same total degree, the degree of this thing 1, 1, 1. So that is a guarantee that the method of homogeneous substitution will work. So that means what? We take y over x as our new variable, which means y is x times v, which means y prime derivative of first times second plus x v prime. So what we have is that this expression is same as this. So I have v plus x v prime is equal to minus 6 over. No, this is v minus 5. Is that right? Instead of that, I wrote v. So at some stage, you have to have your new v and then the basic variable from the previous stage, whatever you had in the denominator here, shows up here. Notice that the y disappears from our equation. You cannot have 3 variables all mixed up. You have to settle it down to 2 for the problem can be handled by standard means. Now what? Well, we are going to do separation. Separation means x has to go one side and v to the other side. So first I take the v to here. So we are doing basic algebra now. This is not differential equation. You're just doing basic algebra. V minus 5. Then I have brought v to the other side as well. Let's take a common denominator. V minus 5. I have minus 6 minus v times v is minus v squared, and minus v times minus 5 is plus 5v. Let's write this thing a little bit more civilized way. So I am going to multiply numerator denominator by minus. Traditionally we start with the highest exponent with a positive factor if possible, and line them up in order. So minus 5v plus 6. So I multiplied that by minus. To multiply this one by minus. Not a significant thing, it's just to make it look nice. Now remember what this means. V prime means derivative of v with respect to x. And we found this thing to be v squared minus 5v plus 6 or 5 minus v. Do you see that this is separable? All homogeneous equations end up being separable. I can put the x's to the right and the v's to the left. So I cross multiply, so it becomes 5 minus v over v squared minus 5v plus 6 dv is equal to dx over x. Okay, so from here to here we have done algebra. What is next? Integrate. Why integrate? Because we managed to separate x and v. Once we manage to separate x and v, then we are in business. Essentially the problem as far as the ODE concerned is like here's the light at the end of the tunnel. We see that, okay, go ahead and calculate this integral and then you'll be home. Well, of course the devil is in details. How do you calculate the integral? How do you handle this one? That one of course is easy. It's just a logarithm. How about this one? Okay, that's where the rubber meets the road. It's like what do you do? What do I do here? If you have this is called the rational function. Ratio of two polynomials called rational function. Rational function. First line of attack is to break it up if it's possible. We had an example like that before. It was called what? Do you remember what was the name of the method? So the idea is that if you have a ratio of two polynomials, try to break it up. Why break it up? Because, well, once you break it up, pieces are smaller, more manageable. It's more likely that you are going to find the antiderivative of the pieces easier. Like here, didn't you see right off the bat this is a logarithm? Why? Because it's such a simple thing. This is also a fraction, but a bit more complicated than that. So the idea is to take that, break it up to pieces like that. Well, break it how? Fortunately, this thing factors. Isn't it interesting? It factors, well, the numbers were chosen so that it would factor, so that we are not suffering too much. So it factors how? It factors, of course, v minus 2 in v minus 3. So idea is that if you had a fraction like this, it must have come from two simpler fractions with these two denominators such that their least common denominator was that, and numerators were kind of combined and cleaned up and boiled down to this. Okay, so we factor this thing, allocate as denominators. Now fight starts. Well, what is in the numerator? Well, we don't know what is in the numerator, and for that reason, we just put some a and b, and now we say, okay, find what is a and b. Okay, now that problem becomes something from pre-calculus. How can I find a and b here such that the two sides are always equal for all values of v? That this is an identity. It is actually always equal to that. Well, standard, there are many shortcuts. You might have seen it in your various classes, but here's the standard way. So it's not a shortcut way, it's a standard way. Put them back together, add them up. Well, what would you do when you're adding them up? You are going to multiply a times v minus 3 and b times v minus 2. So you're taking common denominator. We don't know what the a and b is, but we can go ahead and multiply anyway. Now the statement is that whatever this numerator is has to be exactly what that numerator is. So let's go ahead and clean this up. I say, okay, if I factor the v's, I have a here and I have a b here, so I have a plus b. And then what is left? I have minus 3a and minus 2b. Okay, everybody saw what happened here? So minus 3a, minus 2b. So what did we do? We rearrange this thing in terms of powers of v. Why do we do that? So that if this wants to be identical to that, then the coefficient of v has to be equal to coefficient of v here, and the constant has to be equal to the constant there. That is the reason we did it. So it means a plus b, coefficient of v has to be coefficient of v, and whatever is left, minus 3a minus 2b, has to be whatever number I got over there. Okay, now when we do this type of problem, it's like layers of onion. You remove one layer, you cry a little bit, and then there's another layer, and then you cry a little bit over there, and then you cry a little bit more, and so on. So here we have now cry over solving a system of equation. But that's a simple system. You have seen this kind of stuff in high school. If this problem was bigger, then our system would be a lot more crowded, and in that case you need perhaps linear algebra or something about solving the system. But this is straightforward. Let's go ahead, for example, cancel the b, eliminate b between these two equations, or you can go ahead and eliminate a between the two equations, whichever is your preference. So suppose I want to eliminate a. So I can multiply this by 3. So it becomes 3a and minus 3a cancel each other. So 3b and minus 2b becomes just b. 3 times minus 1 is minus 3 plus 5 becomes 2. So I already have my b. Now I take my b and put it here and solve for a. I get my a is equal to minus 3. So what did we discover? What we discovered is that that expression I had over there, minus 5v plus 6, is equal to a, which is minus 3 over v minus 2, and the b, which is 2 over v minus 3. So what did we call this? We are going to see this thing over and over again in this course. Partial fraction decomposition. So we are decomposing a rational function in terms of pieces that are smaller fractions. What is so great about that? Well, great thing about that, I can integrate these things easily. These are as easy as this one is, but the original one was not so easy to solve. So that problem that I have here is equivalent to saying I have minus 3 over v minus 2 plus 2 over v minus 3 dv is equal to dx over x. Okay, we are almost there. We just integrate everything straightforward. Minus 3 logarithm of v minus 2 plus 2 logarithm of v minus 3 is equal to logarithm of x plus some constant. I put everything in absolute value so that we don't have issues with taking logarithm of negative numbers and stuff. Okay, is that our solution? Well, that sharp onion has a couple of more layers to it, and so you have to cry a little bit more, and then we are all going to be done. So what is left? The original problem was in terms of x and y. X and y, those are our variables. V was for our convenience. So this is not the solution yet. So what do? I do back substitution. We go back to, so all of these problems has a back substitution step to it at the very end. So y over x minus 2 plus 2 logarithm of, again, y over x. Remember, v was chosen as y over x, so we are putting it back, is equal to logarithm of x plus c. Okay, you can kind of declare victory and say I got my solution here, and well, I got my solution. You wanted the relationship between x and y. Here's the relationship between x and y. But you look at it and say, well, this is looking quite ugly. It's like, what's going on? So can we simplify? So it comes another layer of that that famous onion. Simplify. You remember those problems in algebra you had in high school or pre-calculus classes? So there is always an open-ended invitation by the master simplificator. Says, okay, simplify. We have to take a chance to go out, see if we can actually make this thing look any better than what it is. Sometimes it does simplify, sometimes it doesn't. It's very hard to tell ahead of time. So you have to try. Simplify. So what do we do? Simplify. I can write this thing minus 3 logarithm of minus, okay, I can do like that. Do the same thing here. Y minus 3x over x is equal to, there's nothing to do on the right hand side. It's as simple as we can make it. Is that any better? Not really. It's about the same level of complication. Well, we remember rules of logarithm. Logarithm of a ratio was logarithm of a minus logarithm of b. So I write minus 3 logarithm of numerator minus logarithm of denominator. Let's see if that helps. We see a bit of a light at the end of the tunnel since this is here and that thing over there. So some simplification bound to happen. 2 times logarithm of numerator y minus 3x minus logarithm of denominator sorry, is equal to logarithm of x plus c. So open it up. Minus 3 logarithm of y minus 2x plus 3 logarithm of x plus 2 logarithm of y minus 3x minus 2 logarithm of x is equal to logarithm of x plus a constant. It so happens 3 here, 3 here, 2 here, and 1 here Well, they cancel out, is that right? Okay, we didn't expect that, but it happens here. So minus 3 logarithm of y minus 2x plus 2 logarithm of y minus 3x is equal to a constant. Well, this is a tad bit less crowded than what we had here. Okay, we had something here. We are making some improvement. We are cleaning this thing up. Anything else we can do? Well, another rule of logarithm is that logarithm of a to power of k is same as k logarithm of a. So I can take these factors and put them as exponents. Let's see what happens. Y minus 2x to the power of minus 3 plus logarithm of y minus 3x to the power of 2 is equal to constant. Now this became a practice from pre-calculus. What else do you remember? Logarithm of a plus logarithm of b is logarithm of ab. So this is a logarithm of, let me write this one, y minus 3x to power of 2. This power of minus 3 means denominators, all right? Y minus 2x to power of 3 is equal to a constant. Can you guess what am I going to do next? Well, if you have logarithm of a is equal to b, then exponentiate both sides. A becomes exponential of b. So here I exponentiate, so I get y minus 3x squared over y minus 2x cubed is equal to exponential of c. Whatever c is, exponential of that is going to be some number, some positive number. You might as well call it by something else if you wish, or leave it as it is, k. Well, we are almost there. This is a fraction equal to k. You might as well write it as y minus 3x to power of 2 is equal to k times y minus 2x to power of 3, with k is some positive number. Okay, this is where I stop, because if I try to do anything to this, it foams up, gets uglier, it doesn't get any prettier. So this is our final solution. Final solution. You notice that the algebra of this problem was more than the differential equation of it. The differential equation was relatively straightforward, but well, maybe they are equal levels of complication. What else do we have here for us to do here? So okay, two examples from the homogeneous method. If your dy dx is can be written as a fraction. Okay, so we did two examples from homogeneous. Let's go take a case of this one. You look at that, you see, of course, it's not homogeneous. It's like if you write y prime, the powers do not match. It's not a function of y over x. So what do we do? So here we have another problem, x y prime plus y is equal to y to power of minus 3. Now, I know the engineer crowd here, so why are we looking at these type of problem? This one came from study of aerodynamics type of question. So it's not coming out of some curiosity, it's good by itself, but the idea is that if you have an object moving in air or liquid or something and facing drag force, and then you want to find out the trajectory of this object, you come across equations that look like what we are considering. So Bernoulli's equation can be applied to cases of analyzing problems in dynamics with some drag force. Typically, drag force is taken to be proportional to velocity. Well, that's a very simple picture. And the reality is so much more complicated. Well, what's a drag force? Like when you stick your hand out of a window of a car, you feel a pressure on your hand. Faster the car goes, the higher the force on your hand. And the question is, what is this force? Of course, all moving objects, cars, airplanes, everything are going to face this type of force, and you want to know how it's going to influence the trajectory of the object. So, simplest thing is to say that force is proportional to velocity. That is good to some level, but the picture is so much more complicated. So, next level up, as a matter of modeling, people consider velocity and another factor of say velocity cubed or something, and that would be the beginning of Bernoulli equation. So we are looking at a mathematical version of it. For the time being, we put aside the origin of the question and all of that. We are just looking at mathematical manipulation. Okay, how do we solve this differential equation? So this is an example of a Bernoulli type substitution. Bernoulli's idea is, it turned out actually there were many Bernoullis, many smart brothers contributed to the history of mathematics and physics. So which one of those Bernoullis it was, I don't remember either, but it was a Bernoulli. Bernoulli's suggestion was take your v to be y to power of 1 minus whatever you see here, 1 minus whatever you see there. Now, why is this any good? What does it do? So for a moment, let's suppose v is a function of y, is y to power of 4. So, and y itself is a derivative, is a function of x. So if you want to calculate v prime, what are you going to get? You're going to get 4 y cubed y prime. Now this is very significant. Why? Let's go ahead to the original equation and divide both sides by this term, or if you wish, multiply by, let's write it, divide by y to power of minus 3, which is the same as multiply by y cubed. What happens? This becomes x y cubed y prime, multiplying by y cubed, this becomes y to power of 4, multiplied by y cubed, this just becomes 1. Okay, you might say, well, you rearranged all of these things, good for you, what is so great? What's so great is that, remember, we call this one v. Okay, that's all of a sudden so much simplification. And y cubed y prime is stuff that's sitting right here. That is going to be v prime, so y cubed y prime is just v prime over 4. So that is going to be, I had an x v prime over 4. And plus this equal to 1. Now, isn't this so much more pleasing on the eye than the original was? So we actually managed to simplify things. Well, we still have work to do, which is, how do you solve this? Well, let me see. Can you pause this thing for a second and think about how would you actually solve this equation? So again, we are dealing with one of those onions. We apply substitution, problem becomes some other problem. Now we have to solve that problem. So there is always something inside something else. Okay, and did you decide what kind of an equation this is going to be? This is, of course, a linear equation. So remember when we were talking about methods that we had separation, integrating factor. Integrating factor is what was applied to the linear equation. what we have right now is linear. Well, what was the first step of linear equation? Standardize it by divide by this term. So I multiply to make it 1. I multiply by 4 over x. So just to make it standard, v prime plus 4 over x v is equal to 4 over x. Is that right? So if we multiply that equation by 4 over x to get this. Now what? Now integrating factor was exponential of the integral, if you remember from last time. So this becomes exponential of 4 logarithm of x, and we write that as exponential of logarithm of x to power of 4, and that one exponential of logarithm is just x raised to power of 4. So the idea was to multiply this thing by x to power of 4. So what do I get? X to power of 4 times v prime, x to power of 4 times 4 over x times v, and is equal to x to power of 4 times 4 over x. Hopefully you do it faster than I did. So x to power of 4 v prime, this is 4x cubed v, and that is 4x cubed. Can you take it home from here? What did we do? Pause this thing and finish this problem. This is x to power of 4 times v prime, and that is 4x cubed. Now I integrate both sides. So on the left hand side I will have x to power of 4v. On the right hand side, antiderivative of this thing is just x to power of 4 plus a constant. I divide by x to power of 4, so I get v is equal to v is equal to 1 plus c x to power of minus 4, as I divided by x to power of 4. Now I come back and say, well, remember what v was. V was y to power of 4. So what I have here, the y to power of 4 is equal to 1 plus c x to power of minus 4. Or if you wish to avoid negative exponents, doesn't make any difference. Here is our solution. The solution is, of course, a implicit one. We have to take a fourth root out of that. So in a textbook or in the software, you might see something like this: y is equal to plus or minus, and then, so if it insists on finding y, it might set the problem up like this and put the plus or minus for you outside, and then here, of course, you have to have 1 plus c over x to the power of 4 in the fourth root. Somehow you have to have a fourth root. Either way, so if it asks for a solution, you give the implicit one. If it sets it up with a plus or minus, that means explicit can be done, and then you carry it out. Okay, so that is so by now we have 3 down, 2 to go. Next one is going to be okay, so these two were examples from homogeneous. This was Bernoulli. This one obviously fits the category of this linear substitution, that you see a linear expression raised to some power or something done to it, and then that is our next attempt to. That's going to be straightforward. Well, the substitution is going to be straightforward, but from there on, again, we are being challenged by problems of calculus, really. So problem 4 is y prime is equal to 18x plus 2y plus 7 squared. I don't have any story to tell you of where does this thing come from. It's more like we can't do it, so let's list it here as a substitution, as an example of substitution. Where it's going to be useful, well, you go ahead and find out if it is going to be useful somewhere. It's very common in mathematics that mathematicians think about a concept, and a century later the physicists or engineers come across it and say, oh, this is very useful for me. So even though the person who thought about it at the beginning had no intention of any application, it might be applied at some level. So here the idea is substitution is very loud and clear. It's whatever you have here in the parentheses, there's your u. We always want to tie it to the original problem, which has a y prime in it. So I need a y prime here, which ties it to u prime. So u prime, meaning derivative of u with respect to x, is, well, derivative of 18x is just 18. This is 2y prime. Derivative of 7 is 0. So y prime is really u prime minus 18 over 2. So here I put u prime minus 18 over 2, and right hand side, well, you're not going to write that. We spend all this energy calling it u. That's where we are going to harvest that effort. It's going to be u squared. Okay, so that's our new equation. U prime minus 18 over 2 is u squared. Again, let me ask you to pause this thing and solve that problem. What method is applicable here? What can I do at this stage? So, okay, so did you pause and work it out? And you're checking to see if your ideas were correct. U prime is 2u squared plus 18. So let's just remind ourselves what this means. This means du dx. Let me factor a 2 here for nicety. What is this? This is separable. Let's separate du over u squared plus 9. And let me write dx here. This is easier without the 2 to handle. So, without further ado, we can integrate both sides. So, antiderivative, again, you need to have a table of these formulas from your calculus 1 and practice it. So do you remember what that one was? You do a substitution perhaps, or you just use your tables, which is this is 1/3 of tangent inverse of u third, and that is 2x plus a constant. Well, I might as well write this thing as tangent inverse of u third is equal to 3 times 2x plus c. And then I write it as u third is equal to tangent of 3 times 2x, 6x plus 3c. Now, let's remember what u was. U was that expression 18x. Well, let's clean one more step. U is 3 tangent of 6x plus some constant. U was, what was u? 18x plus, what is it, 2y plus 7 is equal to 3 times tangent of 6x plus 3c. So what happens, we can actually isolate y. So I have 2y is equal to minus 18x minus 7 plus 3 tangent of 6x plus some change. So my y becomes minus 9x minus 7 half plus 3 halves of tangent of 6x plus 3c. Now it is customary to say c is a constant, triple of it is some other constant, so the presence of that 3 over there is not helping anything for us. We might as well rename this whole thing, whatever it is, to some constant. Just use one letter k or c or whatever. So again, c is a constant and a multiple of it is some other constant. since we don't know as yet what that constant is, we might as well just wrap it up under one letter and just call it by that letter. Okay, so method of substitution applied to the equations where the right hand side is a linear mixture of x and y, has to be same linear x mixture wherever it shows up, and that substitution is going to be straightforward and you're all there. So the challenge again is, well, what kind of integration you're going to face. Some problem easy and some problem are harder. Okay, the last that I have listed here doesn't fit in any of these categories. It's just listed as one of the, I guess, maybe challenge problem or something, or just to make you think. Well, all of these problems are made to make you think, but this one doesn't match any of those methods we have talked about. This substitution here, at least I didn't see how homogeneous or Bernoulli or linear would apply here. So you have to think for yourself, well, what kind of a substitution would work here? So I strongly recommend that you try to do this problem and then come back and check it. Okay, so here's again a very strong suggestion that you try to do it yourself and then come back and check your ideas, and perhaps maybe to get a little bit of a clue here and then try to do it yourself. So problem 5, x y prime is equal to y times logarithm of x y. Okay, so we try, is this separable? Well, no, it's not separable. Is it homogeneous? We tried, it's not homogeneous. Is it Bernoulli? No, it's not Bernoulli. Linear? No, it's not linear. So what then? It's none of the above. It looks like to me it's none of the above. So we look at that. See, it's inside the logarithm. We try this. Maybe it works. Maybe it doesn't. You have to see. So I take as my substitution, I say u as logarithm of xy, or perhaps you could have taken xy itself, which means xy is equal to exponential of u. So y is a function of x, so x times y is a function of x. Logarithm of it is some function of x, therefore u is some function of x, and it shows up in this manner. Okay, once you decide on a substitution, you're investigating if it helps at all or not. You have to tie it to your original problem. Your original problem has a y prime in it, so here we have to extract the y prime and see what happens. So I differentiate both sides. So I say derivative of first, which is 1 times y prime, that's y prime by 1, plus x, excuse me, sorry, I misspoke. So derivative of x is 1 times 1 y, plus x times y prime, so this thing shows up, thankfully, is equal to, well, derivative of exponential of u. What is that? It's e to the u times u prime. Derivative of exponential of u, eu times u prime. Okay, so what I want in my equation is xy prime, which is e to the u prime minus y. So this is going to be used here. So exponential of u prime minus y is equal to y, and that logarithm, we called it u. Okay, now what? Let's rearrange. E to the u prime is equal to y plus yu. Well, that is y times 1 plus u. Now the problem is that I have a u, I have a y, and this derivative is with respect to x. So I have to get rid of y and just have an x in it. So what is my y really? My y is e to the u over x. Is that right? My y is e to the u over x. My y is e to the u over x. 1 plus u. So let's write e to the u prime is e to the u over x times 1 plus u. Thankfully, this cancels. So I have u prime, let's write it, du dx became 1 plus u over x. Isn't that nice? Now du over u plus 1 is dx over x. I wrote it in a differential form. Now I can integrate. What does that give me? Well, logarithm of u plus 1 is equal to logarithm of x plus a constant. Well, you have equation of logarithms. Let's exponentiate both sides. So logarithm of u plus 1 in exponent is equal to logarithm of x plus c in the exponent. Remember, this splits, but splits into multiplication. It's not addition here. Don't make a mistake there. This is a multiplication. Now, exponential of c is some constant. Let's call it that. Exponential of logarithm of x and exponential of logarithm of u. So what we have is u plus 1 in absolute value is equal to some constant times absolute value of x. What does that mean? It means u plus 1 is equal to plus or minus some constant times x. Now again, you notice that this, to remove the clutter we called it k. To remove this clutter we might call it m or some other letter you wish. So I have u plus 1 is equal to, now m is positive or negative, some constant, let's call it just m times x. Now who was u? By now I forgot what the u was. U was logarithm of x times y. Logarithm of x times y plus 1 is equal to mx. What does that mean? It's logarithm of x times y is mx minus 1. We are chasing y, so let's write exponentiate both sides. So xy is exponential of mx minus 1. I want y, so exponential of some constant times x minus 1 over x. It's rather magical that we can actually get to the bottom of this problem. So every now and then you have to make your own substitution. So we say that there is this idea of substitution, and here we have to create our own substitution. Either x times y or the logarithm of that is helpful in this problem. If you have some other solution method, I'd like to hear about it. Okay, so let's see what happened. There's a long list of methods for solving differential equations. Excuse me. There's a long list of solution methods. This is an extremely huge class of equations. We can take a stab at some small pieces of it. So we had separation, integrating factor, exact equation, substitution. And for substitution, we mentioned 3 well-known substitutions, and every now and then have to make your own substitution. Now, more often than not, none of these methods are going to work. Okay? If you just pull an equation out of a hat and you give it to me, chances are better than 99% I wouldn't be able to solve it, because it just doesn't lend itself to the functions that we have investigated and we know about. Just like, you might have a few keys in your pocket, that doesn't mean you can open every door that ever going to be created by just these few keys. So that would be unreasonable to expect such a thing. What is the remedy? What is to be done? Well, the rescue is the Euler method, or numerical approximation, which is a course all to itself. We have a course on numerical analysis called 4315, Math 4315. I invite you to take that course. It tells you all these problems we have been solving all the way from pre-calculus through calculus 1, 2, 3, linear algebra, differential equations. If we pass the level of introductory problems, how do we solve them? Well, the answer is that you can't solve them. You have to settle for a numerical approximation, and there is an art to handling that, and we are going to talk about that a little bit in the next lecture. But for much of the course, our emphasis is on methods that can be woven out of algebra, pre-calculus, calculus, to solve problems of differential equations. So our emphasis on the style of solution methods we had today, but we also prepare you for the reality out there that you're going to come across an equation that cannot be solved by any of these methods. Okay, until next time, good luck and God bless.